Welcome to the lesson, Gravity in the Solar System, where you will learn about the role gravity plays in the formation of planets, stars, and solar systems, and how they behave in orbit. The vocabulary words for this lesson are gravity, orbit, aphelion, perihelion, centripetal force, solar nebula, and planetesimal. You can click each word to learn more about it. When you go around a loop in a roller coaster, what keeps you in your seat? The seat belt, or bar, of course, is for safety. But what is that force pressing you against the back of your seat? Where does it come from? Johann Kepler, who lived from 1571 to 1630, was an astronomer who was trying to figure out the motion of planets. He and others knew they moved around the sun, but how? And why? He was also a mathematician, but he could not make his math match what he observed. In the early 1600s, working with the records of Tycho Brahe's observations, the answer dawned on him. Click to see what he learned. An orbit is the path that a body follows as it travels around another body in space. In Kepler's time, astronomers knew this, but they couldn't predict the path and speed of the orbits. They thought the orbits were circular. Studying Tycho's data and observations of Mars, Kepler finally realized that orbits were not circles. They were ellipses, oval-shaped figures, and the sun was not at the center. Here is Earth's elliptical orbit. Kepler's realization that orbits are ellipses made sense of data and observations that had previously seemed confusing. Kepler's first law of planetary motion states that orbits in the solar system are ellipses, with the sun at one focus. Each orbit has a far point, called the aphelion, and a near point, called the perihelion. Because ellipses can be described mathematically, so can the motion of planets. Kepler matched observations of planets to the mathematical qualities of ellipses. Click play to see what he figured out. Imagine a line connecting a planet to the sun at some point in its orbit. After the planet moves along its orbit a little farther, imagine another line connecting it with the sun. These two lines to the sun outline an area. As time passes, more areas are formed by placing lines in the ellipse. The shapes of the figures were not the same, but the areas were equal. Kepler's observations and some calculation showed him that the motion of a planet swept out equal areas in equal times, wherever the lines were set. In order for the orbiting body to sweep out equal areas in equal times, it must speed up along some parts of its orbit and slow down in others. And that is just what Earth does as it travels around the sun. When Kepler had figured this out, he could begin to explain the motion of planets. Kepler went further with mathematical analysis of ellipses and time. Click to learn what he found. Kepler discovered that there was a relationship between time and distance, and he produced a third law. The square of the time needed by a planet to orbit the sun is directly proportional to the cube of the planet's average distance from the sun. This ratio is the same for all planets. The math shows that the closer a planet is to the sun, the less time it takes to travel around it. In addition, if you have one piece of this mathematical puzzle, you can figure out the other. Kepler's law made it possible to calculate and predict behavior of orbiting bodies. Kepler's third law is useful today. For example, if the orbiting space shuttle wants to speed up to catch the International Space Station, it drops down a little lower in orbit, a little closer to Earth, and goes faster. Another example is a Global Positioning Satellite, or GPS, that stays in the same place over Earth's surface because its distance from Earth makes it move at the same speed that Earth rotates. Kepler figured out how orbiting bodies act, but what causes them to move as they do? Click the images to learn more. When you ride a roller coaster, you travel along a curved path. Centripetal force is a force that makes a body follow a curved path. You may have heard of centrifugal force, but that is not really a force. It's just your body trying to go straight. If centripetal force didn't keep you on a curved path by pulling you towards the center, you'd fly off in a straight line. Gravity pulls from all directions and towards the center of a mass. English scientist Isaac Newton used Kepler's laws to show that planetary motions were the result of the way bodies with mass attract one another through gravity. Newton developed the law of universal gravitation to describe gravity's effect. The force of gravity acting between one object and another object is proportional to the product of the two masses, and inversely proportional to the square of the distance between the centers of mass of the two bodies. An increase in the mass of either body increases the force, and an increase in the distance between the bodies decreases the force. Newton's law of universal gravitation depends on which of these? Click all the correct answers, then click OK. That's right. If the mass of an object increases, so does the force. If the distance between the objects increases, the force decreases. Also, if the distance between the objects decreases, the force increases. Let's see what you've learned about the main idea of Newton's law of universal gravitation. Look at this figure. What happens to the gravitational attraction if the mass or the distance changes? Consider cases in which each becomes greater or lesser. Type your answer in the box. Click OK when you're finished. You have learned a lot about the motions of objects in space. You've learned a lot about gravity and the solar system. Let's take a quick look at the main points you covered. Kepler's laws of planetary motion describe the motion of planets. Planetary orbits are elliptical. Newton's law of universal gravitation states that any two objects exert gravitational attraction on each other. Gravitational attraction depends on mass and distance. Where do we go from here? Further out into the galaxy and further back into the past. You have been learning about gravity and how it works. Now let's see what role it played in the birth of the solar system. What do you think this image is? Do you think it's on Earth? In fact, this is an image of part of our own galaxy, the Milky Way. This is a region about 5,000 light years away called RCW38. New stars have recently formed in it, and this infrared image shows them clearly. Our own sun may have formed in a region like this one a few billion years ago. How do you suppose it might have happened? How did our solar system begin? Click the images to see. The solar system began as a rotating cloud of dust called a solar nebula. A few billion years ago, in our own Milky Way galaxy, there were small lumps of gas and dust. Small is a relative term, because the clouds or lumps were probably between 7,000 and 20,000 astronomical units, AU, across. Something, perhaps a shock wave from a nearby supernova, caused one of these gas and dust lumps to collapse on itself. Following the laws of physics, the lump began to rotate. As it rotated, it flattened out into a disk. The cloud spun faster. The particles began to bump into each other, and the temperature rose. Gravitational attraction continued to pull everything in the spinning cloud toward the center. Eventually, gravity did cause the center to collapse. This disk would become our solar system. the solar nebula has collapsed. Click the images to see what happened next. When the center region collapsed, it began to spin faster and its temperature increased. The heating, spinning, collapsing process eventually produced a protostar. A protostar is a star that is not hot enough to begin fusion, the atomic reactions that fuel the sun. The protostar continued to gain mass and to grow hotter. Gravity continued to make the ball contract. The center, where most of the mass collected, became increasingly hotter than the surrounding disk. Finally, the center grew so dense and hot that fusion began. Hydrogen atoms fused to form helium. The fusion process released huge amounts of energy. The new star was born. When the fusion process ignited and the new star began to burn, it gave off a powerful stellar wind. The stellar wind blew away the remaining clouds of dust and gas. How were planets born? Click the images to learn more. Use the up and down arrows to see them all. After the solar nebula collapsed and the disk began to rotate, areas of dust began to come together away from the disk's center. After the center collapsed and fusion began, the disk became a protoplanetary disk. A protoplanetary disk is a rotating disk of dense gas and dust that surrounds a newborn star. Planets may form in a protoplanetary disk. Away from the center, planetesimals form. Planetesimals are small solid objects larger than 1 kilometer during the nebula phase that can be somewhat larger later. The planetesimals began to collide and stick together. As they grew larger, their own gravity attracted them into more collisions. They continued to grow. As the disk's center became even hotter, the planetesimals continued to grow. While planetesimals grew, thermal energy from the protostar increased, melting ices in the inner part of the disk. This was the beginning of the inner solar system, the terrestrial planets, and the outer solar system, the gas giants. What's next? Click the images to learn more about the inner and outer solar system. The protostar heated the inner part of the disk enough that ices and gases could not condense. Only rocky materials and metals condensed. So rocky, metallic planets formed in the inner disk. These planets became terrestrial planets. The terrestrial planets differed as a result of thermal energy, pressure, and added mass, as heavier elements sank towards the core. In the cold outer disk, ices and gases could condense around rocks and metals. Gas giant protoplanets formed. These protoplanets had more gaseous material available, so they collected huge atmospheres. When the protostar gained enough mass and pressure to begin fusion, it ignited and became our sun. When the sun ignited and began to burn, a strong stellar wind blew away any material not taken by a protoplanet in the disk. What remained was a young solar system. Over time, more collisions changed planets and orbits and formed dwarf planets, moons, and asteroids. Today, planets, dwarf planets, moons, asteroids, and dusts are all part of the solar system. Click the correct answer for this question. What is a star in which hydrogen fusion has not yet begun? Right you are. A protostar has not yet begun fusion. Click the correct answer for this question. Which force is important during the creation and formation of a new solar system? Try again. Gas pressures do not help solar systems form. Sorry, that's not correct. Planetismals are not forces. That's right. Gravity is the force of attraction between all matter. Remember this image of young stars? The universe is a big place, and formation of new stars and solar systems is taking place somewhere right now. How likely is it that there is another planet like Earth out there? Type your answer in the box. Click OK when you're finished, and then move to the next screen. You have learned a lot about the formation of the solar system. You know that the solar system began in a region or cloud of gas and dust. Gravity played a major role in the formation of the sun. Gravity also played a major role in the formation of the planets in the solar system. Let's review what you have learned about gravity and the solar system. Planets move in elliptical orbits around the sun. Gravity determines the size, speed, and distance of those orbits. Solar systems begin in regions or clouds of dust and gas. Gravity sets in motion the formation of solar systems. Now that you've finished this lesson, if you wish, you can go back and review any part of the lesson again.